6.1 Absolute Extrema. This is a rehash of chapter 5 from the first derivative, but now essentially we're just adding in endpoints. So then it's just like the extraness of checking endpoints. So hopefully nothing too crazy in this section for you. It's just more of what you are already familiar with. Okay, so officially, absolute extrema. Compute the absolute extrema of functions. Understand the difference between absolute and relative, sometimes known as local. Apply the extreme value theorem and then apply the critical point theorem. So we'll get into the theorems later on. They're nothing too crazy. But absolute max or absolute min. So again, absolute should be a hint, right? Like the most, the least. Absolute, right? It is the absolute. Let f be a function and let c be a number in the domain of f. Then f of c is the absolute maximum if f, oh, a maximum of s, excuse me, if f of x is less than or equal to f of c for all x in the domain. Basically, if it's the tallest, okay? So like there's nothing taller, nothing above, absolutely nothing above. There might be equal to, but not above. And then the same thing, but then below, okay? Nothing, nothing. It is the lowest, okay? The lowest, absolute, the max, the min. So identify the absolute extrema of each function if it exists. Then remember that the absolute max and absolute min are y values. They occur at x values. So that little bit is a hint that says we usually say like max of blank at x equaling blank. So max of a y value, I'm just going to say y sub I at some c. We usually use c, right? So some max of like how high, how low. So height, I'll put it that way. And then horizontal location. Horizontal location. Okay, so basically height and then horizontal location. Okay, so the first one, I want actually pause the video. I want you to try all three of them on your own, right? Worst case, you're wrong by yourself. Oh no. See. So here for the first, oh, I guess pause and play when you're ready. And then here, notice that we have an absolute max. What is that? 3 at x equaling -2. And an absolute min of -1 at x equaling +2. Yes, we have endpoints, but again, notice that everything is respectively above or below our max and min. Then rolling right along, we have an absolute min of what is that? -4 at x equaling 2, but no absolute max. Why do I know that? How do we know? The arrows, the fact that it says like basically don't stop going up. Our range is from -4 to infinity, right? So no absolute max because of the arrows. Notice the difference between the arrows and the filled in circles, right? Endpoints versus arrows, right? Endpoints versus positive or negative infinity, up or down forever. So the last one, again, notice we have arrows. So there is, let me choose a color. There's no absolute max or min because we go down forever and up forever. We would say that we have local or relative, local min and max. Okay, right? Because we can look and say, like, okay, yeah, so for this general area, I have a max and a min. But for the whole thing, the whole graph, No dies. So basically, what I want you to notice, what I want you to take away, if I haven't honed in, look, do you have endpoints or do you have arrows, right? Endpoints or are you going on forever? That's the kind of the biggest difference in this whole section. Extreme value theorem. A continuous function f on a closed interval a to b will have both an absolute max and an absolute min on the interval. These extrema will be at critical points or endpoints of the intervals. So what this means is that for the first derivative test, you find your endpoints, or excuse me, find your critical values, your CVs, but additionally, check your endpoints. Check your endpoints. Okay, so this says basically this example right here. Right, so here, these are my CVs, my critical values. But we always need to check our endpoints as well, like what's going on here. Because it could be where we have example, well, that was way too big. Let me erase this. It could be some situation where I have, let's say, here we go. Here we go. I have these as my endpoints. So we would get critical values here and here. But actually, this would be my absolute min and my absolute max. So the extreme value theorem says, well, you got to check your endpoints if you have any, because your cutoff might be above or below your critical values. Like, yes, your critical values are maxes and mins, but we have now changed them into local or relative max mins. So let's put it into action. So find the absolute extrema of f of x equaling x squared minus 6x minus 9 on 1 to 8. So again, at the end, we will need to find what is f of 1, or we could do it now even, and what is f of 8. So we just do that by popping it in. Let's see. So f of 1, so that is 1 minus 6 minus 9, negative 14, and then 8. So that is 64 minus what, 48 minus 9, 7. All right. So we found f of 1 is negative 14. We found f of 8 is 7. So that's our endpoint values, right? The values of our endpoints. So now we're going to do the first derivative test. So, I should remind you, hello. Remember, step 1, find f prime. 2, set f prime equal to 0. 3, solve. 4x, or the variable, whatever it is. All right, so back at it. So f prime of x is what? I want you to be saying it out loud to your computer. Then we set it equal to 0. And then we solve. So add 6, divide by 2. So we have a critical value at 3. So this is a critical value. Now we'll do a sign chart. We'll do a sign chart to see, is it a max or a min? So x, f prime, and f. Again, I think some of y'all don't want to do the sign chart with f on it. That's totally fine, right? Just having f prime on it is good enough. So if I do a test value of 0, I'm going to pop it into this version, that top one. So that's a negative, because that's 0 minus 6 is negative 6. Then if I do 10, 20 minus 6 is positive. So I am decreasing, then increasing. So this is a min. So now we need to find out, well, what is the value of f of 3? What is the value f of 3? So that would be, let's grab my handy-dandy calculator. So 9 minus 18 minus 9 is negative 18. So we now have an absolute max, min, absolute min of negative 18 at x equaling 3, and an absolute max of 7 at x equaling 8. Ta-da! How was that? Not too crazy, hopefully? No? Okay. Let's see. I want you to pause the video and try 3. It's not too crazy. Or I don't think it's anything crazy. Maybe you disagree. All right. Here we go. Remember, find f prime. So f prime of x is equal to 6x squared. 27 times 2. 7 times 2 is 14. 54. Y'all are screaming at me. I know. My mental math skills could be better. 0 equals, and then what? 6 can go into all of them. I'm going to factor out a 6. So x squared, and then 9x and 8. Because 6 times 8 went to the store and came out 64. Or 48. Oh, man. Did I get that all wrong? Yeah, 48. There you go. 6 times 8 went to the store and came out 48. That sounds wrong, but that's how I remember it. Anyways, my brain's so weird. So what two numbers, back to factoring, multiply to 8, but add to 9, 8 and 1, negative and negative. So 0 product principle, right? Set each term equal to 0 and solve. Says that we have, zeros or critical values, at 1 and 8. So we need to test. Actually, you don't need the sign chart. All you really need is to check f of 0, f of 1, f of 8, and f of 10, because then basically the outputs will tell you, how high or how low are you. So you don't have to do the sign chart. I'm going to do a little bit of, not cheating, but I'm going to throw it into my calculator just so we can move this boat along. So 2x cubed minus 27x squared plus 48x minus 15. Fiddle farts. Y'all were hopefully screaming at me this whole time. 2x cubed. Okay, move that over. Minus 27x squared plus 48x minus 15. Let's check. 2x cubed minus 27x squared plus 4x minus 15. I'm going to go second table. I have it on, I just keep my calculator always on ask. So 0, enter, 1, enter, 8, enter, 10, enter, delete. This is just saving me from popping in the function. So f of 0 is negative 15. Then it was 8. Negative 333, 235. Let me just double check. And we're just testing 35. Okay, I knew that felt weird. Negative 15, 8, 335. Okay, that's a 5. How did I get these numbers? Again, just by popping in 0, 1, 8, and 10 into the function. I just used my calculator. You can't do that for the test. You have to put it in. So sorry. Just trying to move notes along for you. Okay, so now you just look, the lowest is this one. So this is my absolute min. The highest is this one. So this is my absolute max. Huzzah! You're done, right? Like that is it. That's all I need you to do. Just check your endpoints. Okay, check your endpoints. All right, now a fun, funky one. We haven't worked with radicals or rationals here in a minute, as fractions at least. So let's have some fun. First, we find f prime. So this is 2/3 x. Remember, -1 is -1/3. And then minus 2x. Set it equal to 0. I'm going to rearrange it so that we recognize what's actually going on here. This is 2/3 times the cube root of x minus 2x. Okay. So I'm going to add over the 2x. Equaling 2/3 times the cube root of x. And then I'm going to cross multiply. Think of this, remember that's over 1. Cross multiply. Yeah. 2 times 1 is 2. Then this is 2x times 3x to the 1/3. I'm rewriting it this way because remember, when the bases are multiplied, you add the exponents. So it says 2 equals 6 times x to the 4/3. Now we're solving. Wait. So this divide by 6, that's 1/3, right? 2/6 is 1/3. X to the 4/3. So just want to raise both sides to the 3/4 because power to a power we multiply. So 4 times 3, so I mean 4/3 times 3/4 cancels out. So we get that x is equal to 1/3 to the 3/4. So this is the 4th root of 1/3 cubed equals x, or the 4th root of 1/27. And since it's an even root, it's technically plus or minus. Okay, since it's an even root, it's technically plus or minus. Okay. All right, so, sorry, that's something that looked wrong. I was like, oh, it's the x equals. Now we have our potential critical values. We just need to check our endpoints. So that is f of -2, f of 2, and then check f of -4th root of 1/27, and f of the positive 4th root of 1/27. Don't worry, anything on the test won't be this crazy. Remember, this is crazy because it's your notes. And I want to show you crazy on the notes so that when you get to the homework and the test, it doesn't feel as bad. Okay, so caret 2/3. Here, let's just even go even further. Caret alpha y equals to get that fraction. 2/3, there we go. Minus x squared. I'm going to go second table. These up. -2 to negative math 5, the 4th root of 1 divided by 27. It doesn't like that one. I must have popped it in all weird. Negative math 5, the 4th root of alpha y equals 1/27. Why are you giving me error? You should not give me error because it is roughly, I have it in my notes. This should be 0.2963, and this is 0.2963. It's because it's an even function. Okay. Oh, and this is, did I not write it down? Negative 2.413 and the negative 2.413. There we go. So we actually have two. So we have two absolute mins and two absolute maxes. And that's okay because notice their height is the same. Their height is the same. So that's why it's fine. This graph, yep, it looks like that. It looks all crazy, doesn't it? If you zoom in. I remember it like it has a little dip between the missing part. I don't know why it's being all wonky though. Oh, okay. That's because it's popped in weird. Let me show you. I know I'm being nitpicky. I want to show you though. X raised to the 2/3. Oops. X raised to the 2/3. Move that over. Minus X squared. That's much better. Yeah. Oh, okay. Oh, yeah. That's okay. Yeah. It has a little like heart situation. Isn't that so fun? So that's why it's the endpoints. Right. See if I can get negative 2 and 2 on the screen. There we go. So that's why we have the endpoints. Okay. You have the little like reverse heart. I don't know. Like a wonky heart. So that's why you're the endpoints, right? Your left and right. And then the top of your hearts, the crescent. The crest, if you would. Isn't that kind of a fun graph? Oh, second table. There you go. Oh, there it is. Much better. Okay. Back to here. So, long story short, check your endpoints, find your critical values, check your endpoints. That's it. It's the same as what we've been doing. Okay, critical point theorem. Suppose a continuous function f of x on an interval I has exactly one critical point at x equaling c. Then f has an absolute extreme value occurring at x equaling c. So a really simple example of this is like y equaling x squared, right? Just a plain quadratic. Looks like this. 0, 0 would be our critical value, right? That's because that's our min, right? So that's what the critical point theorem says. This is a quadratic. It is continuous on an interval. So unless I close it off, unless I add endpoints, we have for sure a max or a min if I have a single critical value. Okay. Because then we just have the one. It's either the max or the min. That's it. So if we look at a more complicated version, find the absolute extreme value of f of x equaling the natural log of x over x on 0 to infinity. It has this domain because remember that the domain for general logs only exists on the right-hand side, right? This is the domain for a log function. So that's why we have that specific domain, 0 to infinity. Okay, so the rules are the same, right? 1, f prime. 2, set the sucker equal to 0. 3, solve. This is where I think it's so much fun and where you might hate me, but that's okay. That's why I'm here. All right, so we need quotient rule. Remember, quotient rule says f over g prime is f prime g minus g prime f all over g squared. If at this point quotient rule isn't somewhere in the forefront of your brain, become more familiar with it. Like make a note card or a flashcard. Okay, I know there are like flashcard apps. Try them out. So f prime of x, f prime of x. So remember the numerator is f, the denominator is g, so that's 1 over x times x minus 1 times the natural log of x all over x squared. The hardest part in there is remembering that the derivative of the natural log of x is 1 over x. But I got you. That's why I'm here. Sorry, I need a sip of water. Don't listen. Then hopefully we recognize that this is just 1. Anything over itself? So this is 1 minus the natural log of x all over x squared. So now we are going to set it equal to 0 and solve. Bear in mind that this right here, right, x squared equaling 0 is at x equaling 0. But our domain does not include 0. So you can essentially ignore the denominator, okay? You can ignore because not in domain. At least the troublemaker number of 0 isn't in the domain. We'll put it that way. The number that would give us issues, 0, is not in the domain, okay, up here. So we just have to worry about setting the numerator equaling to 0 and solving. 0 equals 1 minus the natural log of x. So I'm just going to add the natural log of x over. So the natural log of x equals 1. What undoes natural log, or what's the assumed base of natural log? E. So I'm going to take e of both sides. Remember, whatever I do to one side, I do to the other. E and natural log are inverse functions of each other. So that's why those can just disappear. So this just says x equals e to the first, which is, of course, just e. So we do have one critical value at x equaling e. Okay, so what does it say? It says, suppose a continuous function f on an interval I has exactly one critical point, then it is an absolute extrema. We just have to determine, is it a max or a min? So you get to, I know, you're so excited, you get to make a sign chart. Just going to plop E on there. Remember that E is approximately 2.718. My brain always tries to invert the 1 and the 8. Forgive me, that's why I paused. So I'm going to use 1 as a test value, because remember, 0 is not in our domain. 1. So if I pop in 1 into our derivative right here. And another thing that's nice about 1 is that, I'm going to put it in the cloud, the natural log of 1 is 0. Did you remember that? The natural log of 1 is 0. That's another great thing about 1. So lots of refreshers here. So this inevitably is 1 minus 1, which is 0. Divided by 1. I guess I should choose a better one because 0 has no sign. Let's choose 2. 2 is fine. The natural log of 2. Grab my calculator to show you. Clear. Natural log of 2 is a positive number. So this is just looking here. This is a negative divided by 4. Right? No, hang on. What was it? Oh, positive. Let me just write it down for you. Hang on. There we go. Overlap. So 0.69, 1 minus 0.69 is a positive. Over 4 is a positive. So we've got positives. Then if I choose 10, that's 1 minus something over 100. So what's the natural log of 10? 2.3. So 1 minus 2.3 is a negative number. So this is indeed a max. So not only is it a max, but it is the absolute max. Okay. So we have an absolute max of, we'll find that in a hot second, blank at x equaling e. Now let's find what that is. So what is f of e? Natural log of e over e, just plugging it into the original. Well, the natural log of e is 1 over e. That's it. All right. So the height is 1 over e. I know that might not like mean a lot to you, 1 over e, but remember that's approximately 1 over 2.718. Okay. So like 1/3ish, right? 1/3 if we round up. That's it. Let me make sure. Yeah. Applications, we will definitely do this in person because these are AKA optimization problems. And it might be the hardest section in the whole class. So I definitely don't want to do that on this. I want to do that with you in person. And yeah, that's it. Okay. Yeah, I'll stop talking.